Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest. Find the subarray with bitwise and closest to k. The problem can be solved in very different ways. In this video, we'll be looking at two different approaches. One, using binary search and a range query data structures. In this case, it can be solved using segment tree or even prefix sums as well. And second, we will be solving this problem without binary search with some observations. If you have solved the problem in one way, I would encourage you to at least watch the other solution to the problem, because that will help you add one more tool to your toolbox which you can use in future contest. Having said that, if you are not able to solve this problem, stick till the very end, and I'm very sure you will be able to learn few new things from this video. So with that, let's get started. The problem states that you are given an array nums and an integer k. You need to find a subarray of nums such that the absolute difference between k and bitwise and of the subarray of element is as small as possible. So you need to figure out a subarray such that if you do and of all the element in the subarray, the absolute difference between that value and k is as small as possible, right? So let's take an example. Let's say this is a subarray 1 2 3 4 5. This is the array, and you have to figure out one subarray of this array such that the difference is as small as possible. So if you take this subarray, let's see what will be the bitwise and. Bitwise and of 1 and 2 is 0. So 3 minus 0 is 0. 3 minus 0 is 3. So the absolute difference is 3. But if you take, let's say, this subarray 4 and 5, bitwise and would be 4, and the difference between 4 and 3 will be 1. So 1 is smaller than the previous value you got with this subarray. So this subarray is actually better than the previous one. In the same fashion, you can try out all different possible subarray. You will observe that only the smallest value that you are getting is 1. You will not be able to get an absolute difference of less than 1, and hence the answer here is 1. So hope the problem statement is clear. Now, what is the brute force solution? Brute force solution could be very simple. You can try out every possible subarray, right? So you can maintain 2 pointer and then try out every possible subarray. For each subarray, you figure out bitwise and, right, subtract it with k, find the absolute difference, and keep taking minimum, and your final value would be the minimum possible absolute difference. So this is like the simple pseudo code for this approach. The time complexity here would be order n cube, because you have two nested loop, and inside that you are also figuring out the bitwise and of everything between L and R. That will take order n time in worst case. This can easily be reduced to order n square by removing the loop that we have here. How? We observe that when you are going from L to R, everything between L and R minus 1 is something you already have bitwise and for. So what really is needed is the contribution of the extra element R. So let's say you already have bitwise and of L and R, right? Now you go to another R. Let's say you increase your R and you go to another R. Now you want bitwise and of this entire thing. So instead of finding out the bitwise and from start, you can simply reuse this bitwise and it with this new element, and you will get the bitwise and of the entire array, right? So you can reuse the computations and simply remove this extra loop from here, and the pseudo code would look something like this. Just keep on doing bitwise and for the new element, and this and will contain the bitwise and all the way up to R, right? So from this we can reduce the complexity from order n cube to n square easily. But even this n square is not sufficient, because the value of n is 10 power 5. So we need to optimize this. Now how to optimize. There are two n's. One n is coming from iterating over all the L, and one n is coming from iterating over all the R. If you have to reduce it, you need to remove one of the for loops. Removing any for loop is identical. So let's start by removing, or let's try to remove this inner for loop for now. So what we are saying is, we will still iterate over all the L's. That is, we will still iterate over all the starting point of the array. But I will not fix, or I will not try out every possible ending point of the array. And because I can't afford iterating over all the ending point, this in turn means that among all the ending points, I need a way to efficiently figure out what will be the optimal R without actually iterating over all of them, right? So I would encourage you to pause and try to think what exactly we can do here. So one of the way would be, you are doing a linear search for R, the best R. Is it possible to do a binary search? If yes, then we know that we can simply reduce this loop to a binary search, and instead of order n, we will have order log n, which is very small compared to n, right? So let's see. So first of all, for binary search, the array should be strictly increasing or decreasing, right? Is it the case here? So what the answer is, you can't simply go over all the R's, because we can clearly see that these R's doesn't follow any order. So you can't have strictly increasing or even increasing or decreasing array here, right? So what are other things? One other thing which you can do binary search on could be the value of AND itself, right? Because this is what you are interested in, and what you finally want is the closest value to k, right? So it will also make sense to simply do a binary search over the value of AND and just figure out which of the value is closest to k. Okay, so what does that mean? This means that let's try to enumerate an AND value for every possible L. So for L equals to 0, this is your AND value, which basically means for this L to this R, if you do bitwise AND of everything, you will get 9. Similarly, from this L to this R, if you do bitwise AND of everything, you will get 1. Similarly, for this L to this R, if you do bitwise AND, you will get 0, and so on and so forth. So similarly, this one, second one, denotes the value when L is equals to 1, right? So if you do bitwise AND of everything between this L and this R, value will be 5, this L and this R value will be 4, right? And so on and so forth. Now notice this carefully. These array are actually decreasing. They might not be strictly decreasing, but they are decreasing, and hence if we want to apply binary search here, we could apply easily, right? Now where from we are getting this array, that's a different question. We'll worry about that in a bit, but for now what we notice is, if we have this AND array for a particular L, let's say we are trying to solve for L equals to 1, so we have an AND array for L equals to 1. Now if we have this AND array and we need to figure out the best possible index for the current L, can't we do this? We can simply figure out which one is closest to k, and that will be my answer. And what is closest to k means, in other words, it is simply upper bound or lower bound, whatever you call it. You can simply figure out that, and you will get which element is closest to 4. In this case, you will get this element is closest to 4, and hence you can simply subtract these two values to get the final minimum difference that is possible between k and any bitwise AND, right? So what will be the pseudocode? The pseudocode would look something like this. You will first build this AND array. So how to build this AND array, we'll come to that. So after that, what is there, we simply iterate over all the L. Now instead of iterating over all the R, we simply figure out R by doing a binary search over AND of L for the closest value of k, right? And whatever index we get, we simply take the AND of L to R from that index, subtract it with k. That will be our minimum absolute difference. And there's one more caveat here. R is just the element greater than k. You can simply do, you can check this condition with R minus 1 as well, because that's the element which is equals to k or less than k. So you have to do both the things, but for now I've just shown one part of it, right? You can simply repeat the exact expression with R minus 1 as well, and to get the value which is lesser than k or equals to k, because if you look at this array and if I ask you tell me the value which is closest to 4, so if you go via this approach you will get 6, and if you get 6 you will say okay, closest to 4 is 6 minus 4, 2, but it might happen that you have a 3 here, right? So you will simply check the other one as well before returning 2, because that might also be the smallest possible value. So what is the time complexity of this entire approach? We are doing two things. First, we are building this AND array, right? So we'll focus on that in a bit. Second, we are iterating over L and then doing a binary search. So the second part is simply order and log n, which is efficient, which we can afford and that we can have in the complexity. Now what about this AND array? Notice this, if you build this entire AND array, this is no different than what you are doing here, right? So it will be order n square if you do it, if you need to build this entire AND array. There is no other way less than order n square, because you will have to fill n square boxes. So you will at least iterate over n square boxes once to fill them in. So if you build this entire AND array, this the complexity would be worse than what you had before. Before you just had order n square, but now you have n square plus order n log n, right? So clearly you have to skip this. In other words, you need to figure out a way where you are not building this entire AND array. But now you might be thinking, okay, why this AND array was required? Because you are doing a binary search. Now can you do binary search without building the array itself? I would strongly encourage you to pause and try to think a bit. So notice that we show AND array here just to visualize that okay, with the AND will be strictly or will be decreasing, if even not strictly, but it will be decreasing array. Now we don't really need to calculate all the indexes of this AND array. Why? Because when doing binary search, you will only be touching log n number of indexes. So why even compute all the indexes for all the else? We'll simply compute the indexes which we need. So let's look at that a bit. So we had this algorithm. Now we are saying that we'll build the entire AND array, but is it needed? The answer is no, because for each L you are doing a binary search. So for each L you will be needing only log n number of elements from this AND array. If you have this log n number of elements built already, you are good. You don't need to build all the n elements for every index, right? So if you look closely, we have simply expand this upper bound algorithm. It will look very similar to this. We will start with L and R and we'll go with mid and we'll check if and value of start to mid is less than equals to val or not. If it is, we will search in the right half, otherwise we will search in the left half, right? Now notice for this start or for this L, we only need log n number of values because there will be log n number of distinct m's, right? So can you compute these log n values efficiently? So the answer is yes. You, instead of building this entire array, you can do a range, you can use a range query data structure to figure out what will be the value of and of start to m. And how you will do this? You can either use segment tree that will give you the and of anything between any L and R in just log n time. So this entire thing you will be getting in log n time, and the complexity of upper bound will become log square n. Why? Because you are iterating over, so this loop will take log n time, and inside this loop previously you are accessing a index of an array, but now you don't have that value, you want that value to be computed, and to compute that value you are saying that you can use a range query data structure to compute it in log n time. So the overall complexity of this entire upper bound will now become or log square n, and the overall complexity of this entire algorithm would become order n log square n, which is sufficient to pass the given time constraint at least, because n is just 10 power 5, so n log square n would be sufficient. Now how to figure out, like if you know about segment tree, this is very straightforward problem. You can simply put the array in segment tree, build the segment tree on bitwise and you are done, right? But if you don't know segment tree, then also you can solve this very easily. How? What you want bitwise and, right? Now what is bitwise and? Let's say you want bitwise and of everything between this L and R, right? So let's first try to expand this into the bits, right? So this 9 is 1001, this is like 2 power 3, 2 power 2, 2 power 1 and 2 power 0. So if you want bitwise and of everything between this L and this R, what you want is bitwise and of everything between here, and you can do bitwise and of every bit independently and figure out whether it will be 1 or 0, right? Now when does a bitwise and will be 1? Only when there is all ones, otherwise it will be 0, right? So what you really need is, you really need to find out how many ones are there in first bit, how many ones are there in second bit, again in this range L to R, how many bits are there or how many ones are there in the third bit, and finally how many ones are there in the fourth bit. And whichever value is equals to the number of numbers, in this case number of elements here is 5, so whichever of these is equals to 5, that is the bit which will be set in the final bitwise and all other bits would be 0, right? So what you can do, you can simply build this entire array and build a prefix sum for this array, and once you have prefix sum, whenever someone say okay find me out the bitwise and between, let's say L and R, some L and R, or let's say L dash and R dash to not confuse it with the original L and R, you can simply go to the prefix sum, figure out the number of ones between L dash and R dash, and if it is equals to the number of elements between L dash and R dash, you can set that number in the bitwise and, otherwise you can keep it unset, right? So that way what you need is, you need order number of bits operation to figure out which all bits will be set, and once you figure out which all bits will be set, you can simply compute the number based on the by setting those bits, and once you have the number you can simply use that here, right? So just to reiterate, this we want and bitwise and between start and m. Let's call start as l dash, let's call m as r dash. So we want bitwise and between l dash and r dash. This you can do using segment tree in login operation, order login time, right? Or this, if you don't know about segment tree, you can simply do a prefix sum for each of the bits, and for each bit you can figure out how many ones are there, and if the number of ones is equals to the number of elements, you will set that bit, otherwise you will keep that bit unset. So this entire thing would take order b time, assuming that the prefix sum is already built out. You can pre-build it before even starting this algorithm. So either you can answer it in log n or you can answer it in order b time, and both of them would pass the given time constraint. In this particular scenario, order b is slightly higher because 10 power 9 order b would be 30, whereas order log n would be log of 10 power 5, which will be around 20. So in this particular scenario, it will be slightly better if you use segment tree kind of approach, but even this will be passed. You can use this prefix sum approach as well. So now we know how to solve this problem in n log square n or n log n into b time, where b is the number of bits. So I am not showing you the code for this because the code would be exactly equals to what we have shown here. We will simply iterate over all the else and then do a binary search for r, and while doing binary search just use segment tree or this bitwise prefix sum data structure to answer the value of and at a particular position. So next we're looking at the second approach. The second approach, we don't want to figure out the bitwise, like we don't want to do a binary search, right? And we want to reduce the complexity. So let's start again from the beginning. So we had this order n square algorithm, right? And we want to reduce this. So another approach could be, okay, let me see what are all different possible values of and for all different possible values of r, and if I can enumerate those different values efficiently, then also I can remove this loop with those different values, right? So that's the thought process. So initially we started with, okay, I am doing a linear search, so can I do binary search? But now we are saying, okay, let's say you're not able to figure out that, okay, binary search, you can do binary search over this AND array by not building the AND array initially, but rather by lazily building it while it is required. So if you're not able to do that, then second thing that you might think that, okay, can I figure out all distinct values of bitwise AND here? And if I can figure out all distinct values efficiently, then also I can remove this loop with some other factor, right? So that's what we are trying out. So we know that we'll be starting from this L, right? Let's say this is L. So we are starting from here. Now we will be taking the bitwise AND of every different subarray starting at L and going over R's, right? Now from L, what all different values you will get? So you have this bitwise number which is 9. So from 9 you might get a number which has one of these bits or all of these bits unset. Notice that you will never get a number which have a bit set which is not set in this L. Why? Because when you are doing a bitwise AND, a bit will only be set if it is set in both the numbers. Then so in this case, if it is not set in L, it will never be set again, because even though R has this bit set, the bitwise AND would not be 1, right? So from this L you might either be getting this, or you might be getting this where this bit is unset, or you might be getting this where this bit is unset. Now if you think about it, there might be 2 power b number of possibilities, right? You can have b number of bits here, and one of these, like any of the combination of these b bits can be unset, right? So if you think naively, there can be 2 power b different values from here, and if you iterate over all 2 power b values here, this will be worse than what you have before. You had order n square before, but now instead of iterating over r, you are saying I will iterate over all these 2 power b values, and these 2 power b values will be bigger than r in most of the scenarios, right? So this will not work, right? And second problem with this approach is we are not sure which of these values are feasible. You have this array, right? Now among these distinct 2 power b values, which of them you will get by doing bitwise AND is something you need to check as well. So that is another complexity that you will be having with this approach. Now the biggest thing here is, or the biggest observation here is, you will never be getting all these distinct values. Instead you will be getting one value first, and whenever you are getting one value first, you will have some bit unset there, and once that bit is unset, that bit will never be set again. And if you follow this approach, you will be having only 31 distinct values, not 2 power b, but rather only 31 or 30, whatever you call it, distinct values for the bitwise AND of L and R. I would encourage you to pause and try to think from here onwards by yourself. So just to reiterate, what we are saying is we will never be having all these 2 power b values. Instead, let's say you got this first. Now as soon as you get this, you are sure that you will never get anything else, because everything is 0 here. If you keep on expanding your subarray, you will still be getting 0, right? Now let's say if you get this, now if you get this, no matter what you do, you will never get this one back. So what are the possible choices? Possible choices will be, you will get this exact same number while going further, or you will get this 0 finally, right? In the same fashion, if you get this first, then you will never get these element at all. The only possible choice is you will get 0 after some more iteration over r, right? So what you are doing is, whenever a bit is unset, it will never be set, right? So whenever you get a number, let's say there is 30 number of bits set here, so you can have at max 30 different values. Now what are those values is something which will differ, but you can have at max 30 different values, because in worst case you will be just unsetting one bit here, and then another bit in the second value, another bit in the third value, and so on and so forth, right? Now if you can somehow figure out these 30 different values efficiently, your job is done. For each L, what you will be doing, you will simply be figuring out these 30 different values and then compute the absolute difference with k and take the minimum, right? Now the job is to find out this 30 distinct values. So let's start with L. Which of these you will get first? The answer is the one which will have 0 first in the right. So we have 2 set bits here, right? So let's figure out which one has closest 0. So closest 0 to this is index 1, closest 0 to this is index 2. Now once we know this, we know that this bit will be the one which will be unset first, right? So from this number 9 we will get a number where this bit is unset. So basically from 9 we will get 1 because this bit will be unset. Now after that you will get 0 because this bit will be unset after that, right? Notice that it could have happened that this is all 1. So in that case this bit is never unset, so you will only get 9 and 1 from this L. You will not get 0 at all, but in this case you are getting 0 as well. So basically for this L you can arrange all the bits in the order of their closest 0. So in this case this bit will be the first one which will be unset, and then this bit will be the second one which will be unset, and so on and so forth. So after you get this order you can simply unset the bits in that order to get all distinct values possible, right? Now let's take one more example. Let's say you are figuring out the value for 7, right? So you have 3 set bits here. So let's arrange them in the order of their nearest 0. So in this case nearest 0 is this, in this case nearest 0 is this, and in this case as well nearest 0 is this. So for all of them the nearest 0 is 6. So you can't say that you will unset this first and then you will unset this and then you will unset this. You have to unset all 3 of them simultaneously because all 3 of them will become 0 at the same index. So from 7 you will not be getting 4, 3 or 1, instead you will directly be getting 0, and these are the only 2 distinct values possible if you start at this particular L, right? So hope the overall approach is clear. Now there are 2 ambiguous bits still left. First, figuring out the closest possible 0, right, for each bit, and second, I know that there are 30 distinct values, but whatever computation I am doing, is it still within the time constraint or not? We are not sure about that. So let's look at both of them. First let's look at what all we are doing. We will assume that finding out nearest 0 is something which is efficient. We'll come to that how to find it, but we'll assume that it is efficient for now. So what you have, you are doing something for each L. So first of all you are doing something for each index, so n will be there. Now what you are doing, you are figuring out all distinct values, all distinct 30 values at max, right? So how you are figuring out that, we'll come to that. But after that what you are doing, after you got all 30 values, you are iterating over all those values and taking the difference with k and taking minimum across all of them. So basically you are doing order B operation. B is 30 here, so B is number of bits. Now what is remaining is how to figure out these 30 values. So what we have said is we will arrange these bits in the order of their first 0 occurrence in the right. So if there are 30 bits, there will be an array of size 30 which will contain which position a particular bit is unset first. So in this case the array would contain that bit number 0 becomes 0 bit number 0 becomes 0 at index 1. Similarly bit number 3 becomes 0 at index 2. So this is what you will be building, right? And building this will take order B time because you are building this for every bit. So for each bit you need to first check whether that bit is set or not, and then you will be figuring out what is the nearest 0. So let's multiply it by 0, which basically says what is the time to find out nearest 0, right? Now once you have built this array, you will sort it, right? And sorting will take order B log B time because there can be at max B number of elements in this array, right? So sorting can take order b log b time. Now once you have sorted, you will get get this one of this path, basically the order in which these bits will be unset one by one. So once you get this path, you will simply unset the bit in that order, and that will take you order b time, because at max you will be iterating over b number of bits only. So this is the overall complexity. So let's remove order b for now, because that is not significant number with respect to these two. So the overall complexity is order b cross z plus order b log b plus order b. So let's remove this order b as well from this complexity. So overall complexity is n multiplied by b cross z plus b log b. Now n cross b and n cross b log b is efficient. That is that will pass the given time constraint. But n cross z, n cross b cross z, is it efficient or not? That is something we need to figure out. In other words, we need to figure out the value of z, and if z is also of a low order, this solution would work. Otherwise this solution would not work. So the answer is z is just order 1. Why? Because you can pre-compute what is the smallest, what is the nearest 0 for a particular bit. How? Let's assume that this array is not an independent array. So what we are saying is, you will simply be, so you need to figure out what is the nearest 0 for each of the indexes. So how you will do that? You can simply start from here. Whenever you see 0, you will update your latest 0. So in this case, nearest 0 for this one will be n, or rather 7, because there is no element afterwards, right? Now you are maintaining a value as well that will say what is the 0 you have seen latest. So latest 0 you have seen is at index 7. Now you reach here, what is the nearest 0? That will be the 0 you have seen so far. So you will simply put 7 here, 6 here. This is 6th index, so this is 6th index, so you will be updating it to 6 when you come here, right? And when you come here, you will say the latest 0 I have seen is 6, so the nearest 0 will be 6. Similarly, when you come here, latest 0 is still 6, so the nearest 0 will be at index 6 only. From here, latest 0 is still 6, so it will be index 6. Now because you have a 0 as here as well, so the latest 0 you have seen now is at index 65432, at index 2. That's the latest 654, sorry, that the latest 0 would be at 3. That is the latest 0. Now you come here, latest 0 is at index 3. Now you see again a 0 here, you will update your latest 0 to 2. Now you come here, from here latest 0 is 2, so you will simply mention that the latest index which will have 0 afterwards will be 2, and similarly for this one, latest 0 would be 2. So this is how you will build this nearest 0 array in just order n time, by simply iterating over the array from back to front. And you will build this for each of the bits. So you will take order n into b time to build this entire array of nearest 0. And once you have built this entire array of nearest 0, figuring out what is the nearest 0 to a particular bit at a particular position will just be order 1 operation. You can simply look at this array and figure out that. So this z would be simply order 1. So overall complexity is order n into b to build the array, and then while querying you are doing n multiplied by b plus log b operation, which you can think of as nb log b, right? And this is very efficient. In fact, this is more efficient than the segment tree solution, which was order n log square n, or n log n multiplied by log b, multiplied by b. So we have a better solution than the previous one, right? So let's look at the pseudo code before we jump into the actual code. The pseudo code would be similar to what we just discussed. We will first figure out this array for each of the indexes. This array will contain two things: what is the bit which is set and what is the nearest 0 to it. And nearest 0 you will figure out before this loop itself. How to compute it, we had just discussed that. Now once you have this array, you will simply sort it with respect to the index of the nearest 0, right? And once you have sorted it, you have this array sorted with respect to the nearest 0. Now the element you got first, that will be the bit which will be unset. So in this case nearest 0 was 1 for the bit 0, so you will first unset bit 0. And notice that if there are multiple elements with 1 as the nearest 0, you will unset them all in one single go. So that's why what you will do, you will simply iterate over all the bits which is unset at that exact same position. And once you have all the bits with you which is unset at that position, you will unset all the bit at that position, and you will get one number which you will obtain the very first time while doing the bitwise AND of the subarrays. And once you get this number, you will simply do absolute of k minus array L. So what we are doing is we just update this with to array L itself. So we'll simply do absolute of k minus array L. If you can actually keep a different number and use that here, right? That we are not actually doing array L. Array L is actually the array L with all the bits at the current position unset, right? And after this iteration, you will unset more bits and so on and so forth until you have exhausted all your set bits in the array, right? So this is the overall algorithm, and this will work in NB log p time. So if you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself, because that's the very important piece, as I always keep saying. Let's look at the code. The code is exactly what we discussed. We first figure out closest 0. I think I figured out closest 1 as well, but that is not required here. So how to figure out closest 0? We will simply go over each of the bit, because we need to figure out closest 0 for each bit. If you remember, we had this b number of arrays, so we need to figure out closest 0 for all these b number of arrays. Now for each bit, we will be finding out of building an array of size n. So we'll start from the back and go all the way to 0. Now whenever we are at a position, we will simply update the last 0 that we have seen. Now if at the current position, at the current bit, if the value is 0, then we will update the value of last 0 as well to the current index, and we will simply keep on doing this. And after this iteration, for this particular bit, we will have an array which contains the nearest 0 for every index, right? Now after this, we are simply iterating over all the else, figuring out how many distinct values that can be possible. And for that, we first build all the set bits and the index where they will become 0. So we iterate over all the bits. If the bit is not set, we don't care. If the bit is set, then we figure out the closest 0 to that bit, right, and push it to the array. Notice we are pushing the bit, the index first and then the bit. So when we sort it, it will be sorted by default with the index, which means whichever will become 0 first will be at the beginning of the array. Now once we have this entire thing done, we will simply iterate over these index and bit array and simply check which all, if there are multiple bits which needs to be unset at exact same index. So we have this index, right, and we'll see if how many bits are there which are unset at this particular index. So we will unset those bits which matches the index, move forward. We'll keep on doing this until the index is exhausted. So one example would be this here. So if you figure out the array for this, you will see that bit 1 will be unset at index 6, bit 2 will be unset at index 6, bit 3 will be unset at index 6. So all the index 6 bits you will iterate and unset them all. So that's what we are doing. We are iterating over all the bits with the same index and unsetting them all. So XOR will just simply reverse whatever bit is there at that particular position, and after that we will simply take the minimum, because whatever is contained in value will be the one possible distinct value for this particular L, and we'll simply take the maximum absolute difference between that value and k, and they keep taking minimum across whatever values we have seen so far, and that will be your final result. So hope both the approaches are clear. If you have any doubts in any of the approaches, feel free to ping in the comment section below. I would be happy to answer. If you haven't coded the segment tree or prefix sum solution by yourself, I would strongly encourage you to code that and get it submitted as well, because that will help you understand how binary search works in general. And that same trick, that is, if binary search only accesses log-n number of elements, and if you can figure out those log-n elements efficiently, you don't need to build the entire array. This trick is very helpful in many different problems, so would encourage you to try that out as well. If you face any difficulty, always happy to help in the comment section. So with that, if you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.